Hi, my name is Katja, and I'm an assistant professor in the Foundational and Experimental Security Research Group, which is part of the Computer Systems at BFU. Today, we are going to talk about software quality, more particularly, what quality means in the context of service-oriented design. Let's begin. So why do we care about quality in software-oriented design? Microservices are currently increasing in popularity in industrial environments, being adopted by several big players such as Amazon, LinkedIn, Netflix, and SoundCloud, and many more. These microservices are relatively small and autonomous services that work together, are modeled around a business capability, and have a single and clearly defined purpose. The correct design and implementation of microservice-based products come with a promise of high performance speed, availability, modularity, and the list goes on. But scaling this architectural style is hard. The design can actually become immensely complicated and can play against you. The figure on the slide shows a graphical view of the allowed communication between 1,500 microservices at Monzo, which is a financial software-based company. Now, every line here is an enforced network rule for allowed traffic. Consider how difficult it is to locate a faulty or incorrect rule in such a configuration. Still, many organizations decide to do the shift from a monolith to a service-oriented design. But a misunderstood trade-off or underestimated quality concern in software-oriented design can shift the entire business. Nikki Wrightson is a principal engineer at Skyscanner who hosted a panel at the QCon London Practitioner Conference with participants who have moved from a monolith to a microservice and in some cases back again. So this was actually the case for one of the companies that is called Segment. So a software engineer at Segment reported that one of the driving forces behind the U-turn to a more monolithic approach again was the operational overhead that came with microservices, which was too great, and they didn't have good tooling around testing, deploying, and maintaining these microservices. And maintenance is one of the key quality attributes, as we will see shortly. If you're curious, you can read the discussion online by scanning this QR code on the slide. So inability to assure and maintain quality in a service-oriented design, or any software for that matter, can result in billions of losses. And a prominent example is a loss of security. In their most recent report, Redware surveyed just under 300 executives and senior IT professionals at companies worldwide to document the state of web application security in the era of microservice app development. They actually found that 90% of these participants reported that they had a data breach in the last year. Further, 56% of the respondents were highly confident that they could keep the data of the customer safe. So in other words, the professionals responsible for keeping your data safe feel like they're doing this job with the probability of a toss of a coin. Cyber attacks are very real threats today with dire consequences for the victims. So organizations can suffer major reputation losses, customers demanding compensation, financial losses, lawsuits, and loss of employment in some cases. The reason behind this result, as in the report states, is that conditions nowadays are very friendly to the attackers in the microservice space. There is a variety of technologies that is used, which actually increases the attack surface. There are some unclear security responsibilities, meaning which department or which part of the system should take care of security. And the rate of change is immensely high, which actually also opens new risks. So basically, privacy is a rare commodity in today's digital world, and we know it. Numerous documentary films have explored this theme, and in the last decade, important legislations and privacy laws have actually emerged that aim to protect consumer data. This is an example is the GDPR and the California Consumer Privacy Act. Of course, more research and innovative ideas are needed in this area to build better foundations for our future. But since we're talking about the end of the world, let's focus on what we will learn today. In this lecture, you will achieve the following learning outcomes. You will learn about the software quality and its attributes. In the second part, you will learn about the implications of adopting service-oriented architectural style on these quality attributes. We will also have a look and a dive a little deeper into one particular quality, which is security. And there you will learn the basic concept about security by design. And finally, you will learn about some bad practices or bad smells of service-oriented design, which can hurt particular quality attributes. So let's first define what software quality means to us. Software quality is a study and practice that describes the desirable attributes of software products. Now, what does it mean that there are these desirable attributes? Is this from the perspective of the user or the perspective of the organization? And as we will see, software quality actually has very different dimensions and several. So let's talk about the so-called functional dimension first. In the functional dimension, software quality means the fact that the software is free of errors, that is, free of bugs and vulnerabilities, including missed or misunderstood requirements and errors in the design, functional logic, data relationships, process timing, validity checking, and coding errors. And although there are still some open problems, software engineers have gotten pretty good at measuring functional quality. For instance, in the requirements engineering space, there exist automated or semi-automated techniques that analyze compliance to requirements, such as, for example, traceability approaches. There are also pretty good tools out there that can statically examine the source code, for instance, by observing the abstract syntax tree, to detect not only syntax errors, but also security vulnerabilities or bad practices in general. The second dimension of software quality is the so-called non-functional dimension. Non-functional software quality is the fact that the system has a handle on its technical depth and satisfies different quality and quality attribute characteristics. The quality attributes that we will study are the core part of this dimension. And actually ensuring these qualities in the software that we build is very difficult, and the presence of quality violations is much more subtle. Unfortunately, the reality is not so simple, as quality and quality attributes vary in multiple other dimensions as well. Business and contextual goals drive the trade-offs that directly influence the assessment and the guarantee of quality. For example, safety-critical domains incorporate finer-grained notions of safety and fault tolerance, as well as the ability to certify that these properties are adequately met, whereas in other non-safety critical domains, this is not prioritized. Practitioners have to be prepared to do some trade-offs and continuously monitor the assurance of some levels of quality, the ones that they will not compromise. This process is also called quality assurance. So, can we really achieve perfect quality in our software, or is this just a pipe dream? And if we achieved this pipe dream, was the quality really so good, or was the testing bad? In fact, more often than not, software quality assurance is mostly associated with testing practices. But this is a misconception. Software quality assurance cannot be achieved when confined only to executing tests and conformance activities. Without embracing an ensured by design and implementation approach, along with tools that actually assist developers to accomplish it, achieving software quality will continue to mostly rely on our ability to test extensively. Instead, software engineering practices need to prioritize the application of techniques in which enforcing software quality is already incorporated. And this has to be done in all phases of software development lifecycle. For example, during the planning phase, a quality assurance plan and test strategy are created. Later on in the analysis phase, the specifications are reviewed for quality And during the design phase, the software design is analyzed to detect bad quality practices. Once the system is implemented, test cases can be executed, code reviews can be conducted, and other testing activities can be performed. Finally, quality is also monitored using specialized metrics once the system is actually in production. We are going to have a little closer look at the software quality attributes, their definitions, and their place in the context of service-oriented design. First, a small spoiler. Not all practitioners perceive that microservice design has a positive impact on software quality attributes. This was one of the main findings from an interview study with 17 professionals from 10 different companies. Now, whether or not this is true for any organization, of course, goes beyond the goals of this research that was conducted, and it remains to be seen in the future. However, it is interesting to observe the results that these scholars have gathered in order to reflect upon potential trade-offs that may be making our own design choices with the service-oriented style. Now let's look at the software quality attributes as defined by the ISO 25010 standards about software and data quality, which is a well-established standard available to the public for a good decade. There are 8 quality attributes listed in this standard: maintainability, portability, compatibility, reliability, performance efficiency, usability, security, and functional suitability. Maintainability represents the degree of effectiveness and efficiency with which a system can be modified for improvement, correction, or adaptation to changes in the environment. It's composed of modularity, which is the degree to which a system is composed of discrete components such that a change to one component has a minimal impact on the other components. It's also composed of reusability, which is a degree to which an asset can be used in more than one system or in building other assets. Then we have analyzability, which is a degree of effectiveness and efficiency with which it's possible to assess the impact on a system of an intended change to one or to more of its parts, or to diagnose a product for deficiencies or causes of failure, or to identify parts to be modified. Modifiability is the degree to which a system can be effectively and efficiently modified without introducing defects or degrading existing product quality. And then finally, testability is a degree of effectiveness and efficiency with which test criteria can be established for a system, and tests can be performed to determine whether those criteria have been met. On this slide, you see the reported impact of using a microservice architecture on maintainability. The researchers have found that in many of the migration cases, maintainability was actually the killer attribute. This was either the main migration driver or reported as the most obvious improvement over the monolith. Microservices entail modularity by design, which is one of the subcharacteristics of maintainability. This modularity by design facilitates also agility through independent release cycles. Modifiability was also reported to have improved due to small and independent units. Reusability, on the other hand, was seen as rather ambiguous. One participant explicitly warned against sharing libraries between services. While testability of a single service would be greatly improved, the increased outer complexity could prevent the same on the system level. The impact on analyzability was assessed similarly, and in this context, one of the architects criticized the consequences of separated code repositories per services. The second quality attribute that we will look at is portability. Portability is the degree to which a system, product, or component can be transferred from one hardware or software or other operational environment to another. Portability is further composed of adaptability, installability, and replaceability. Adaptability is the degree to which a product or a system can be adapted or for different or evolving hardware, software, or other operational usage environments. Installability, on the other hand, is the degree with which a product or system can be successfully installed or uninstalled, for that matter, in certain environments. Finally, replaceability is the degree to which a product can replace another specified software product for the same purpose and in the same environment. According to the interviewees in the study, portability would generally profit from container technologies such as Docker and Kubernetes. Some participants tended to attribute it only to containerization, not in particular to the architectural style. Other participants, on the other hand, highlighted better installability, which allowed to effortlessly change the platform. So one of the participants actually described it as follows. So in theory, we could run the system in an arbitrary cloud or on-premise, even though this is more due to containers and not so much microservices. Portability has definitely increased. Adapting and replacing modules were also often reported as improved, but not necessarily for all the modules and for the entire system. Now let's have a look at the next important software quality, which is compatibility. Compatibility is the degree to which a product, system, or component can either exchange information with other products, systems, or components, or perform its required functions while sharing the same environment. Compatibility has the following two subcharacteristics. Coexistence, which is the degree to which a product can perform its required functions efficiently while sharing a common environment and resources with other products and without negatively impacting any other product. And interoperability, which is the degree to which two or more systems, products, or components can exchange information and use the information that has been exchanged. The influence on compatibility was also commonly perceived as beneficial, mostly due to the standard communication protocols. One architect reported compatibility as one of the main drivers for microservices to unify distribution channels on their product. In particular, the ability to coexist and integrate with legacy systems was positively perceived and a strong requirement for many companies during the migration phase. Reliability is the degree to which a system is able to perform specified functions under specified conditions for a period of time. This characteristic is composed of the following subcharacteristics. Maturity, which is the degree to which a system, product, or component meets the needs for reliability under normal operation. Availability, which is the degree to which a system, product, or component is operational and accessible when required for use. In other words, availability is the readiness of correct service and resources. Next, we have fault tolerance, which is the degree to which a system, product, or component operates as intended despite the presence of hardware or software faults. Finally, we have recoverability, which is the degree to which, in the event of failure, a system can recover the data and re-establish the desired state. Reliability is an important quality, perhaps even more so for cyber-physical systems that are running in close contact with us humans. One example is, for instance, social robots. Interestingly, when it comes to reliability, there were two opposing views by the practitioners in the study of Bogner et al. One was that with many microservices, there is always something down. Users just don't really necessarily notice it, since the vast majority of the system is still up and running. The opposing view was, however, that people say reliability increases, but you need a lot of tools and knowledge to be more reliable than you were with your old monolith. And the complexity is definitely increased, even though some stuff is still better. Nonetheless, reliability was perceived as predominantly positive once those obstacles were overcome or features like Kubernetes liveness probes were implemented. Next, we have performance efficiency. Performance efficiency represents the performance relative to the amount of resources used under stated conditions. It's decomposed into the following subcharacteristics. First is time behavior. So this is the degree to which the response and processing times actually meet the system requirements. Resource utilization is the degree to which the amounts and the types of resources that are used meet the system requirements. And finally, capacity, which is the degree to which the maximum limits of a product or system parameter meet requirements. With regards to performance efficiency, the consensus on scalable microservices was confirmed by many participants as the most notable advantage. One architect actually termed it nicely: constant and fast response times while increasing load by a factor of 10 to 100. I believe this is only going to be working in a microservices architecture. On the other hand, efficient resource utilization could suffer from high redundancy to some extent, as was noted by two of the practitioners. One of them saw benefits in choosing the best performing technology for a single service, but many others do not perceive or expect many changes in performance efficiency. Usability is a degree to which a product or system can be used by specified users to achieve specified goals with effectiveness, efficiency, and satisfaction. It's composed of several sub-characteristics, such as how appropriate the users recognize the system for their needs. This is appropriateness recognizability. Then learnability, which is about how easy it is for the specific user to learn how to use the system in a given context. Then we have operability, which is a degree to which a product or system makes it easy to operate. User error protection is another subcharacteristic, which is a degree to which a system protects users against making errors. And then we also have user interface aesthetics and accessibility, which is a degree to which a system can be used by a variety of different types of users. Usability was generally seen as not impacted, or as one of the participants phrased it, in general, end user experience shouldn't really be affected by microservices except for maybe increased performance. Interestingly, one participant even highlighted the suitability and ease of use for A/B testing. Some companies in the process of migrating use this opportunity to also improve their user experience with a new front end. But this could be also attributed to the process of the migration itself rather than the architectural style. Operability, in turn, was described as challenging due to the variety of involved components and different technologies. But in the opinion of the practitioners, it would eventually improve with a high degree of automation or very homogeneous services. Security is the degree to which a system can protect information and data so that the involved entities that are communicating with the system have access appropriately according to the levels of authorization. So there are several sub-characteristics of security. Confidentiality is the first, which is a degree to which a system ensures that data are accessible only to those that have the right permissions. In other words, confidentiality is the absence of an unauthorized disclosure of information. Integrity is the degree to which a system prevents unauthorized access to or modifications of computer programs or of data. Non-repudiation is another subcharacteristic, which is about the ability for the system to prove that certain actions or events in fact took place. This means that there cannot be, after the fact, these actions cannot be repudiated, so they cannot be denied, so to speak. Then we have also accountability, which refers to the ability of the system to trace actions of an entity to that specific unique entity. And finally, authentication, which is a degree to which the system can prove the identity of a subject or a resource. Now let's look again at the study. If we turn back to this study, the results are a little bit more concerning. So security was perceived as twofold by the practitioners. One group actually appreciated the possibility to apply individual security settings to services depending on their criticality. In one case, it helped actually to ensure conformance with the GDPR. Still, no participant explicitly mentioned that microservices would actually ease securing the system. Now, the other group actually stressed that there is an increased attack surface, or as one of the architects phrased it, you put it nicely, before you had to basically secure one door, now you have 20. To tackle security challenges, it is important to avoid bad practices and apply well-understood patterns, such as API gateway. We will learn more about this later on in this lecture. The final quality attribute is functional suitability. Functional suitability represents the degree to which a system provides functions that meet stated and implied needs when used under specified conditions. The characteristic is composed of the following subcharacteristics: functional completeness, functional correctness, and functional appropriateness. Functional completeness is the degree to which a set of functions actually cover all the specified tasks and user objectives. When it comes to correctness, this is the degree to which a system provides the correct results. And finally, functional appropriateness refers to the ability of the functions to facilitate reaching the specified objectives. Functional suitability seems not to be greatly impacted, at least in the eyes of the 17 interviewed practitioners. Some practitioners expect a higher appropriateness and correctness due to a better overview of the individual services and having these services more aligned basically to the business processes. But most of them report that no noticeable impact on this quality. This makes pretty good sense as well, as we already know that the same functional behavior can be achieved with different architectural styles. We are roughly midway into our lecture. If you'd like, if you need, you can take a coffee break, or if you just want to stretch your legs a bit, this is a good opportunity. Welcome back to this lecture on designing for software quality. Up next, we will zoom into one of the quality attributes in particular, that is security. Security by design is a term that is often used in organizations and in the academic literature as well to describe all the methodologies, methods, and techniques that are used to think about security early on and continuously. The idea comes from the fact that if security is ignored and the product is shipped to production with major security holes, it can cost an organization much more to fix it afterwards than it would cost if they dedicated some of the effort early on. Do you remember this slide which we used to list some quality assurance practices? Security is a quality, as we have learned as well, and security engineers, architects, and analysts, they have work to do in every phase of the software development lifecycle. For instance, during the planning phase, they have to create a security plan. Later on, when the design is analyzed, there is risk assessment teams that are conducting a risk analysis, and they set up certain quality gates for the product. During the design phase, the attack surface is analyzed, and people use threat modeling as a technique to think as attackers think and to try to find what kind of attacks are possible and how to mitigate them. Later on, when the programs are actually developed, one can use static code analysis and establish tools and libraries to detect certain vulnerabilities in the code. We can also use fuzz testing and dynamic code analysis for security purposes. And finally, of course, we also should be able to monitor the security status of our product by using tools and methods such as intrusion detection tools and incidents and plan our incident response. Some of the key security concepts that we'll learn today are basically our common vocabulary for any security engineer. So let's begin. First, we have a security goal. A security goal is one such concept that is crucial to understand as a designer. A security goal refers to the protection of an asset from some harm. One can have multiple security goals, and they can be also more specific. For instance, a protection of the customer registration data from unauthorized observer. So the thing that we want to protect is also very important, and usually it's some piece of information, but it can also be something less tangible, like the reputation of a company. But without exception, assets are things that are valuable to some stakeholder of our system. In the security goal, we want to protect assets, but we want to protect assets from some harm, which does not mean physical harm necessarily, but it refers to a loss of one of the security attributes or concerns. This harm needs to have some notable impact on the asset of value, else we wouldn't really care about protecting it from this particular harm. Finally, a security threat is the thing that causes harm. This is basically the secret plan of the attacker, so to speak, or where he or she develops a way to compromise the security concern of an asset. Usually we can describe security threats with scenarios where several actions lead to a compromise. The key thing here is that threats are intentional and they are malicious. So this is not the same as having a software fault, which could also be an arbitrary event. We are talking about attackers that are human or inhuman, but they have certain motivation and means to cause an accident. An incident. So where is the designer in this picture? I like to think of designers as kind of inspectors. Although inspectors will actually investigate a crime after it's committed, whereas designers will try to see into the future sometimes to even prevent a crime to take place. So they will have a crystal ball and they will try to predict what the attacker wants to do. So first thing they have to do is they have to identify the assets of interest. They do this usually by interacting with the stakeholders of the system as part of the preparation or planning for a security design analysis. Further, they have to also understand very clearly the relationship between these assets and the functionalities of the system, which is not always an easy thing to do, especially in a very large and complex organization where there is no single one person that would actually have a good understanding of the overall what's going on. Typically, designers need to elicit this kind of knowledge and information from several domain experts. So once this knowledge is collected, the designer can start to identify security threats. This process is also sometimes called threat analysis or threat modeling. And at the end of this threat analysis, designers need to prioritize the security threats that they found according to some risk levels, which is usually a combination of impact and probability. This will give them the top priorities security threats, which they have to secure the system against. The prioritized threats need to be mitigated to protect the assets that absolutely cannot be compromised. So the designer has to plan for implementing certain constraints in the system or countermeasures to achieve the security goals. This diagram summarizes the relationships between the key security concepts that we just mentioned. So starting from the malicious attacker. An attacker has the means and the right motivations to pose a security threat which causes harm, that is, loss of any of the security attributes which we had CIAA, that may occur to an asset. The asset of value The asset is of value to at least one stakeholder and is related to some functionality of the system which is constrained by the countermeasure countering the posed threat. In the following, we will focus on the building blocks for secure design. So in this figure, we will talk about more the countermeasures part rather than the attacker side. A secure design is built on top of some basic security mechanisms or building blocks, as we will call them. The number one lesson here is that unless you're truly a security expert in building and proving that crypto protocols are unbreakable, you shouldn't try to attempt to reinvent the wheel. So typically, it pays off to be humble in this situation and to reuse sound and existing implementations of security mechanisms. Now, as we've previously said, the security building blocks are ways with which we can achieve the security concerns. So on the right side of the slide, you see these blocks, and here we basically have the how aspect of security. So how do we secure things? On the left side of the slide, we have the what. So basically, what are we securing? Notice also that availability is often also considered as a security concern. So if you remember, according to the ISO standard that we looked at, availability is considered as part of reliability, but practically it's also often considered in security, especially considering so many security attacks that are targeting to compromise this quality. Namely, I'm talking about the variety of denial of service attacks. So let's go over these building blocks one by one. These building blocks can be used to protect one or more of the security concerns. For instance, cryptography is used to protect confidentiality, so to hide information from prying eyes. For this, encryption is typically used, such as the SSL or TLS communication protocols. But cryptography can also be used to ensure the integrity of the information, for example, by using hashing. So in this case, what we want to do is we want to make sure that there cannot be any modifications, either additions or removals to the information we're sending. Finally, it can be used for authenticity, that is proving the origin of a piece of information or software, which can be achieved with digital signatures, for instance. So, for example, also think about the mobile apps that you download from the mobile app store. Many of those apps are actually signed so that the risk of installing a rogue mobile app is lower. The most important thing to worry about for the designer using cryptography is about the cryptographic keys. So we need to ask ourselves the questions of how are these keys or certificates distributed around the system? Where are they stored? And if they are protected during storage or during when they are at rest or when they are being transferred. Using cryptography can help in protecting valuable information in transit and at rest. But remember, it's important to use secure crypto protocols and to make sure to implement them according to the specifications and the suggested way of use. Authentication is a process of verifying identity of something or someone. In other words, it's a claim on the identity assertion via some credentials that you have to show. So these credentials are used to authenticate, can be either something that you are, so here we're talking about biometric authentication, or something that you have, for instance, using a token or a certificate, or perhaps something that you know, for example, your password. The designer here needs to pay attention though when it comes to managing the credentials. Namely, we have to think about where these credentials are stored and where they updated. Is that location in some public domain or is it a secure location? How are these credentials protected? Are they stored encrypted or are they in plain text? And also, is access to them perhaps logged? Finally, is the life cycle of the accounts properly managed? So, how are the accounts created, renewed, cancelled, and locked, for example? It's also a good practice to combine the type of credentials that are needed to authenticate a user. So, for example, using two-factor authentication. First, we can request a password and then also a fingerprint scan or a Face ID scan on your phone. Using authentication helps in making sure that when our services share the data with our users, they're actually not sharing this data with some malicious entity. Authorization is different from authentication. Authorization is about giving certain permissions to system users or system processes. So the permissions can be either to execute programs, write, or read to storage. And the way that we grant access in our system, of course, depends on the user or process roles and the rules that are linking the roles to grant certain permissions. So this is based on certain rules. But in order to grant access, we of course first want to make sure that we are granting this access to the correct user. Therefore, authorization actually requires authentication first. Similar to the previous building blocks, we have actually another asset to protect now. As designers, we need to be careful about these permissions. How do we store the permissions and how do we manage their lifecycle? If the permissions fall into the wrong hands, they can be modified, for example, by the attacker, and it could lead to either a denial of service attack, so that the availability is compromised, or even ransomware or elevation of privilege attacks. Audit trails refer to keeping track of the actions that are performed within the system. They include also the contextual information that is relevant to a specific action, like, for example, who was performing this action and at what time of day they were performing the action. Audit trails can be used as a type of deterrent, actually, to avoid users from ever performing malicious actions. Or in a post hoc way, they can also be used as a form of intelligence to understand how an attack was mounted, what possible traces the attacker has left behind, and ideally, of course, to identify who the attacker is. This kind of analysis is called computer forensic analysis, and it has an important role in the legal systems around the world. It's of course also useful to strengthen our own systems so that they are able to prevent similar kind of attacks from happening in the future. Again, there are a few attention points for the designer that are important to keep in mind here. First is all the important information about the actions actually being logged? And what about the accompanying contextual information? This contextual information must be sufficient and detailed enough to perform the analysis we want later on. This is a pretty crucial point if we want to make something useful out of keeping audit trails, right? Lastly, the audit trails and their access need to be as well protected. Otherwise, we can actually risk that the attacker simply wipes out all the logs that are relevant to the attack, and our efforts will have been in vain. The last of the building blocks is monitoring. Monitoring refers to mechanisms that you have in place in your system to observe an activity. You can have monitoring mechanisms in place on several levels of abstraction, from the network flows, for example, tracking TCP packages, all the way to user activities, for instance, whether or not a user was logged in or logged out. What is important here is that with monitoring, we are using this information to detect malicious behavior. Most of the detection mechanisms can be grouped into either misuse detections, where the system actually has a model of an attack, or rather, the system is keeping a model of some malicious behavior, so a pattern of this behavior. And then the system is proactively looking for patterns of such behavior in the activity stream. And then in contrast, We have anomaly detection. And with anomaly detection mechanisms, the system has a model of normal behavior instead, and it is on the lookout for deviations from this normal behavior in the monitored activity stream. From the design perspective, we should pay attention to the location of the sensors that are actually collecting the activities of the system, where the events are stored, and how the events are processed, as mentioned on the slide. One of the best practices for secure design is to build defense in depth. For doing that, we have a variety of security tactics that we can use on several levels of abstraction. First, we can have preventative controls. These are used to actually resist or avoid attacks before they can occur. For instance, one preventative tactic for secure design is to always authenticate and authorize users to do as little in the system as possible, also called limiting the exposure. Preventative tactics are a very good idea to lower the overall security risk and reduce the costs in reacting to incidents that may occur later on when our products are in production. But if security incidents do happen, it's always a very good idea to be able to automatically detect them while they're occurring and to have a reaction plan as well to set up in place. For example, monitoring the network traffic can help to spot where there is a denial of service attack happening on one of the ports, for example. Once a denial of service attack is detected, an alarm can be immediately sent to inform the network administrators, for instance. And this is basically the reaction plan for this particular instance. Finally, securely designed software has also corrective controls in place to recover from an attack post-mortem. This could include maintaining audit traces, as we've discussed, restoring also from previous states, and the like. The number of controls and the level of depth of defense depends basically not only on the available mechanisms and technology, but also on the budget and the business goals of your software products. If you're curious to read more about building security into service-oriented design, I recommend you to have a look at Chapter 9 of Sam Newman's book, which is entitled Building Microservices, Designing Fine-Grained Systems. You can also find a number of sources for security patterns, which can be also used to plan the security, not only in service-oriented design, but also in general. So I also suggest you to look into some of these sources. Now, to conclude this part, I will invite you for a short thinking exercise. So let's imagine that we are the owners of Music Corp, which is a corporation offering some music products like rare vinyls, CDs, MP3s, and also some music services like streaming online. So it includes several departments. We have a warehouse, finance, web store, and so on, as usual. For this exercise, we're just going to focus on the web store subdomain. So we have standard web browsers that are used by our customers to shop on the site. We also have a third-party royalty gateway. These are companies that will handle royalty payments for a new streaming service. These companies basically contact us occasionally to pull down some records of what music has been streamed when. This is kind of information that we would like to protect as we are worried about competition from rival companies. Finally, we also expose our catalog data to other third parties, for example, allowing the metadata about artists or songs to be embedded in some music review websites. Inside our network perimeter, we have some collaborating services which are only ever used internally. So this is basically the setup. Now the question is, if you put on your security goggles right now, how would you improve this following design? Feel free to also pause the video and to draw a small sketch or to make some notes. After you have the improved sketch, think about all the other quality concerns as well. Do you see any problems with your improved design, and how could you solve it? In the next slide, I will show the solution. So if you want to take an attempt at it, then pause the video now. So here we have an example of how to improve some security aspects in this design. First, for the browser, we decide to use a mix of standard HTTP traffic for some non-secure content and HTTPS for secured logged in pages. This will basically give an extra protection layer to our customers if they are, for example, on public Wi-Fi. When it comes to the third-party royalty payment system, we are actually pretty concerned not only about the nature of the data that we're exposing, but also about making sure that the requests we're getting are actually legitimate. So here, we don't want to compromise, and we insist that our third party uses client certificates. Now, all the data is sent over a secure cryptographic channel, increasing our ability to ensure that we're being asked for this data by the right people, basically. When it comes to the feeds for the catalog data, we want this information shared as widely as possible anyway, and we want to allow people to easily buy music from us. But we don't want this to be abused as well. So we'd like some kind of idea of who is using our data anyway. So here, using an API gateway with API keys is a fairly fast solution that gives us the opportunity to still monitor the sources of the requests. Inside the network perimeter, things are a little bit different, as the chances of someone attacking it are lower since they must be in a very close proximity or have some level of access first. So the attackers that here we are mainly talking about probably are insiders. Ideally, we'd like to use HTTPS as at a minimum, but also managing it partially like that is somehow painful. So instead, let's say that we compromise and we decide to put the effort into hardening our network perimeter, including having properly configured firewalls and selecting an appropriate hardware or software security appliance to check for malicious traffic. So we will do everything that we can. We will do port scanning for denial of service attacks and intrusion detection and so on. Finally, we're not so much worried about the data in the catalog service because after all, we want that data to be shared and we actually provided an API for it. But we're very concerned about our customers' data. Here we decide to encrypt the data that is held by our customer service. And we build also a key management schema to ensure that the secure storage and the use of encryption keys. As for the second question about other quality concerns, your improved design may probably look different, but there is always this trade-off between security and performance. So the most prominent example being that encrypting all communication, also between individual servers, for instance, both for data in transit and at rest, is obviously going to slow down your system for sure. Therefore, we always need to think about building these secure enough systems, as we cannot possibly secure everything to 100%. Much of what we covered here is the basics of how to implement technological safeguards to protect your systems and data from malicious external attackers. However, you may also need processes and policies in place to deal with the human element in your organization. How do you revoke access to credentials when someone leaves the organization? How can you protect yourself against social engineering attacks? As a good mental exercise, consider what damage a disgruntled employee could do to your system if they wanted to. Putting yourself in the mindset of a malicious party is often a good way to reason about the protections that you may need, which is exactly the purpose of doing threat modeling. In the last part of this lecture, we will briefly mention what not to do. Sometimes we use the term bad smells to describe bad practices. Architectural patterns and tactics can help the designer in planning for quality concerns. But patterns themselves are nothing without the context of the domain where they are implemented. Further, there is not a guarantee that the architectural pattern is selected correctly. In fact, many scholars argue that selecting the right pattern in a given circumstance is incredibly hard. Therefore, it is vital to also learn from each other's mistakes and examine some of the bad practices in service-oriented design. Specifically, we will look into the top 5 microservice smells. One example of a bad smell for microservices is having cyclic dependencies, which always hurts the maintainability of the service cluster. We define microservice-specific bad smells, called microservice smells, as indicators of situations such as undesired patterns, anti-patterns, or bad practices that negatively affect software quality attributes such as the understandability, testability, and so on, the ones that we've mentioned already. To identify microservice-specific bad smells, researchers have collected evidence of bad practices by interviewing developers experienced with microservice-based systems. Then they classified these bad practices into 11 bad smells, frequently considered harmful by the practitioners. 5 of the bad smells were reported to be considered very harmful or moderately harmful by more than about half of the participants. The first is making wrong cuts. Wrong cuts turn out to be one of the most frequently mentioned smell and one of the 2 smells considered the most harmful. Based on the practitioner's answers, splitting a monolithic application is always a complex task, especially because developers are used to splitting applications into horizontal layers. So think about splitting it into database and business logic and so on. They tend to adapt such an approach out of habit instead of considering splitting applications based on the business processes. The problem that this may cause is a incorrect separation of concerns and increased data splitting complexity, which can of course burden the performance quality attribute. So what can we do about this? Well, the paper mentions a solution that performing a clear analysis of business processes and the needs of the resources could help in avoiding this smell. But sometimes this is easier said than done, and some organizations may still struggle in making the right cuts, especially if one has a lot of legacy code to operate with. The second most often mentioned bad smell is to have hard-coded endpoints for service locations. This basically means that there is a string somewhere hard-coding the location of a service instance, which can be very, very bad when the location of the service must be changed. So maintainability is affected. A solution, which is a rather common method, is to use a service discovery mechanism to locate your services. A service discovery is a method for application components to locate each other. For instance, a service registry is often kept up to date with currently available instances. Client services can query the service registry before making a request to an available service instance. The third most common bad smell is having cyclic dependencies between services. This means that there is some cycles, so logic of service A that calls service B, which then calls service C, which in the end calls service A again. Having the cycles present means that when updating one service, for example, service A, the others must be also checked as well for compatibility with the new changes that we just made to service A. Obviously, this also decreases the maintainability of the system. A common solution is to try to avoid having cycles altogether if possible, or in the worst case, refine the cycles according to their shape and apply an API gateway pattern which exposes the calls in an explicit format to maintain. Another commonly mentioned and pretty harmful bad smell is shared persistency. Shared persistency means that there are different microservices that access the same relational database, or even worse, the same entities of the same relational database. The problem here is, of course, that this results in highly coupled services accessing the same data, so the teams developing them are also less independent and must coordinate when they make any sort of data operations. This could be very bad for performance, but also for maintainability. There are three possible solutions to remedy this bad smell. The first is to use independent databases for each service. The second is use a shared database with a set of private tables for each service that can be accessed by only that service. And finally, to use a private database schema altogether for each service. Of course, depending on the persistence needs of each service, one might choose one over the other. Finally, not having consistent API versioning was also often mentioned as harmful by practitioners. This means that the API version names are basically not following the semantic changes consistently. So the problem that this causes is, of course, in the case of new versions of non-semantically versioned APIs, API consumers may face some connection issues. For example, the returning of data might be different or might need to be called differently in a different version. So in order to solve this, the APIs simply need to be semantically versioned to allow services to know whether they are communicating with the right version of the service or whether they need to adapt their communication to a new contract. So basically, we need to be diligent in version naming. To read more about microservice-specific bad smells, I invite you to read the article on the definition of microservice bad smells published in the IEEE software. In this lecture, we talked about the many phases of software quality, including the famous 8 attributes for software and data quality. Then we also learned about the possible implications of adopting the service-oriented architectural style on these quality attributes. In the third part of the lecture, we talked about some basic security principles and the security concerns and building blocks for secure design. And finally, we briefly mentioned the top 5 microservice-specific bad smells and how to resolve them. Now, I'd like to leave you with 4 important thoughts that I hope you will take away from listening to me going on and on about software quality. The first lesson is that software quality has multiple dimensions, and it's difficult, if not impossible, to fully achieve it. The second thought is that service-oriented design may have a positive impact on some qualities, but not all of them and not always. The third lesson I would like to leave you with is that the role of the designer is to analyze the system, identify quality goals, implement sound solutions, and apply good practices. And finally, on top of other bad practices in software design, microservice-specific smells can also decrease the overall quality of the developed software. This concludes our journey today. I hope that you learned new things and I hope that you had fun doing it.